In this section, we're going to derive a formula for the length of the graph of a curve y equals f of x on a closed interval from a to b. And we're going to assume a few things. We're going to assume that the function is continuous and differentiable, and we're also going to assume that its derivative is continuous, so that we're guaranteed to get a nice formula at the end. And as we did with volumes in Calculus 1, we're going to use Riemann sums to approximate the length of the curve over the interval, and then we'll take the limit to get an integral which gives the actual length. Well, suppose we have a curve y equals f of x shown in blue here, which extends from the point a, f of a, to b, f of b. And if I want to approximate the length of that curve on that interval, I can do so with a bunch of line segments. I start by splitting up the interval into n equal parts of length b minus a over n. And the endpoints of these subintervals are x0, x1, x2, etc., etc., xn equals b. And I'm going to call the point on the curve above xi, pi. So I have n points on the curve, each one above one of the endpoints of these subintervals. They're called p0, p1, p2, as far as pn, which is directly above b on the curve. And I join these points by line segments, straight lines, for which it's easy to find the length. And as you can see, the larger the n, the closer these line segments are going to be to the curve, and the sum of their lengths will give me a pretty good approximation to the length of the curve between a and b. The lengths of these line segments are pretty easy to calculate using basic geometry. It's the square root of the difference of the x values squared plus the difference of the y values squared for the x values and y values of the endpoints. And of course, the line segment between pi minus 1 and pi is going to have length the square root of xi minus 1 squared plus f of xi minus f of xi minus 1 squared. And of course, xi minus 1 is delta x, and I can pull that out from under the square root sign, and I get the length of this line segment is delta x times the square root of 1 plus f of xi minus f of xi minus 1 over xi minus 1 squared. Now remember the mean value theorem from last semester. Because f is continuous and differentiable on this subinterval, this quotient, this difference quotient, is equal to the derivative of f of xi star for some xi star in the interval from xi minus 1 to xi. And now let's get back to our formula for the length. The length of the blue line, which is the graph of y equals f of x between a and b, is the limit as n goes to infinity, the number of approximating subintervals goes to infinity, of the sum of the lengths of the line segments shown in red here. And now we have a formula for the lengths of these line segments. The ith one is given by the square root of 1 plus f prime xi star squared times delta x, where the xi star squared is somewhere in the ith subinterval. So when we add these together, we get a very nice Riemann sum, and in the limit, the delta x becomes the dx, and the integrand becomes the square root of 1 plus f prime of x squared, and this becomes the definite integral from a to b of the square root of 1 plus f prime of x squared dx. So this method gives us a very nice formula for the length of the curve y equals f of x between x equals a and x equals b, namely the integral from a to b of the square root of 1 plus f prime of x squared dx.